The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. We're going to get started in just a few short minutes here. We're just waiting for a couple more people to come into our webinar. Thanks for holding tight. Talk to you in a minute.
Don?
Yep, I can hear you, Mike.
Okay.
We're going to get started in just about a minute here, and Erica is going to kick us off.
Alrighty, hello everyone who is in attendance for our webinar today. We're going to get things started this afternoon. We have some great guest speakers with myself here, and we're excited to have you here. So if you are here for How Does Wi-Fi Channel Width Affect the Network, you are in the right place, so welcome. My name is Erica Eierman. I work in business development here at 7 Signal. So you've probably received an email or a gift card from me too if you've attended one of these webinars before. So if you have, welcome back. And if not, if this is your first time, welcome. We're really excited to have you. I'm joined here today by two very talented 7 Signal team members that have extensive wireless knowledge. First, I'll introduce Dave Hallis, who's one of our solutions engineer. Go ahead and say hello, Dave.
Hello, everyone. Been here at 7 Signal for a number of years. It's a great place to work. Having a lot of fun. I do have a lot of wireless background. I was at Cisco Systems as under the Aeronet product line, and I was also chair of 82.11i and chair of 82.11eh, and also CWNA.
Awesome. Thanks so much, Dave. We're really happy to have you here with us today. Yep. And then at this time, I'd also like to introduce Mike Graham, who is one of our very talented and knowledgeable sales engineers here at 7 Signal. So go ahead and say hello, Mike.
Hi, everybody. Nice to be here today. Like Dave, I have been at 7Signal for a while. In fact, I think we started within a couple of days of each other. And I also have an extensive wireless background. I've been designing and installing wireless networks since before 802.11. Let's put it that way.
Awesome. Thanks so much, Mike. And we're also really glad to have you on our webinar today. So with that, folks, we're going to get started today. And I'm just going to give you a little bit of background about who we are at 7Signal and why we do what we do. We were originally founded in Helsinki, Finland back in 2007 by Nokia engineers. Then in 2012, they decided to relocate to the beautiful, warm, sunny Cleveland, Ohio, because there was a lot of wireless knowledge in this area as well. With some improvements and achievements we've been having lately, in 2018, we converted to 100% base SaaS solution, and we're also certified in over 40 different countries, so we're everywhere around the world. And also, we manage 4 million global wireless devices daily, and that number is growing exponentially each day as we continue to bring more customers on board with 7Signal. And we also have 11 patents. So that means our solutions have been tested and can do things that many things that other competitors and solutions can't. And to just dive a little bit further into our software as a service solution, we are a proven technology platform, a completely cloud-based experience, and our solutions are going to give you reports, alerting, and analytic tools that can give your wireless teams proactive information into the wireless environment that your environment has. So this is going to be able to tell you what's going on inside your environment, if there's any challenges. It's going to be able to tell you if there's going to be wireless downtime before that even happens. So our tools are truly proactive and intuitive for wireless teams to use. And just looking at some of the testing that our solutions can do, they do throughput, packet loss, latency, and jitter. And it's a one enterprise solution. So our devices are truly packed full of lots of tools that are going to be really helpful and useful when it comes to monitoring your wireless environment. And before we jump into the nitty-gritty of our webinar, I wanted to mention our free regional user groups that we have coming up at the end of this month. July 29th in Denver, where we will be at Kaiser Permanente. We'll have our wireless team members there. It'll be a great event to connect with us and to delve more into wireless knowledge. And also in September on the 17th, we're going to be in Nashville before Wi-Fi Trek. So if you're attending Wi-Fi Trek, please feel free to reach out to myself or anyone at 7Signal, Don Cook, and we can get you set up to connect with us before Wi-Fi Trek. And then we'll also be in Prague in October on the 7th, right before Wireless LAN Pro. So if you have any interest in registering for our free regional user groups, you can register by using the link below, or by reaching out to myself or Don Cook, and we'll be sure to get you registered.
Well, Erica, I just want to let you know I want to reach out to you to go to Prague.
Yeah, I know. I would love to go to Prague. Maybe I can ask my boss if I can go. Alrighty. So with that being said, we're going to jump right into our information and why you're all here today. So without further ado, I'm going to hand the controls over to Mike Graham.
Okay, thank you very much, Erica.
Yeah.
We're going to talk a little bit about channel widths and how they affect Wi-Fi performance, and a little bit about how they work differently in 802.11 AC. So let's see if I can make the page advance. Erica, I'm not sure you gave me control.
Can you use the controls now, Mike?
I cannot.
Alrighty. So I'll advance for you. Just let me know when you want me to advance, okay?
Okay. Oh, somebody else's slide. Great. little bit, we're going to start and talk a little bit about the history, but from the beginnings, 802.11b and G and A were all 20 megahertz wide channels. When 802.11n came out, that introduced 40 megahertz wide channels supporting twice the bandwidth, but reducing the channel count by half. And then 802.11ac extended the principle and introduced 80 and then 160 megahertz wide channels, again doubling and redoubling the bandwidth, but once again cutting the number of individual channels.
Yes.
And did you really mean to do all those forwards there? Erica, can we go back to the?
Yeah, we're going back.
Yeah, we're just trying to make sure we have it all set for you, Mike. Is this good?
That's good.
Perfect. All righty.
All right. So for 2.4, as we see here on the chart, there are 11 channels available, but of course those channels overlap. So in fact, we only have 3 non-overlapping channels, 1, 6, and 11, and that's a real issue whenever you're trying to place access points in an environment and not have those channels coverage areas overlapping. And I think our next slide illustrates that point. I remember, Erica. Yeah. So we can see here on the left with the traditional 2.4 gigahertz, 3 non-overlapping channels, 1, 6, and 11. It's essentially impossible to design a densely packed network where the same channels don't overlap. And whenever those channels overlap, you have to remember 802.11 or wireless networks are a shared medium, just like, you know, good old-fashioned coax Ethernet, if anybody remembers that. So the users that are on channel 1 or 6 or 11 are all going to share bandwidth talking to those access points. So when the access points are in that close of proximity, you multiply coverage, but you don't necessarily multiply throughput because of that overlap. On the right, we see 5 gigahertz, a 5 gigahertz example where there are many more channels. And of course, that's one of the reasons that 5 gigahertz is so much preferred, is we do have the abundance of channels there. And we can see that in this particular example with 9 access points, we don't have any overlapping channels at all. Each access point has a dedicated channel for it, and the users on that access point are only going to have to share bandwidth with other users on that access point, and not every user on that channel in the facility. Dave, do you have any expansion to make on this? I know that you have a lot.
Well, I think you hit on the core issue, and a lot of times people will think, when they think about Wi-Fi, they're thinking about it at home. And so you can see at home, you don't really have this problem because, you know, maybe you've got 1, maybe you've got 2, possibly 3, you know, access points. Typically, people do not have, you know, in their home very many more than that. And that's where they're kind of like thinking of it and saying, well, I don't really have this problem at home. You're right, you don't have it at home. It's because of just this issue, the number of channels that are available to you. But you come into a carpeted office, like, or a hospital or something like this, where you have many more access points. Now you start to run into this very issue.
Absolutely. What's our next slide, Erica? We have some pop-ups. All right. This is a great one that shows what can happen with utilization whenever you have an uneven distribution of channels. And a graph on the right actually shows SSID AP pairs, but it could as easily be channel utilization. And you can see that on channel 1 there on the green is obviously much more heavily used. No surprise there. If those channels were more evenly distributed, of course, we would see a more balanced utilization. And the consequence is, since it all kind of comes down to user experience, is those users that happen to be on channel 1, which will be most of them, since most of the APs are on channel 1, are going to have a much poorer experience than those people lucky enough to connect on 6 and 11. Next up, Erica. All right, a little recap from that first slide. We talked about the wider channels, and in fact, below you can see a 2.4 example where we have the traditional 1, 6, and 11, and the multiple horizontal lines on each of those represent multiple access points. And then somebody's running a 40 megahertz wide channel, which really on 2.4 you shouldn't see, but some access points will run in 40 megahertz wide mode. And it interferes not only with channel 1, or shares bandwidth not only with channel 1, but also with those access points on channel 6. So it really does a lot of damage to twice as many users as it otherwise would. Anything to add on this one, Dave?
No, just the one thing that I point out is it's kind of nice to have it visually kind of come out to you, because that way, a lot of times when you're looking at things, if a system is kind of giving you something in the tabular form where you're just looking at numbers, it's kind of really difficult to kind of figure out, if somebody says, well, you're on channel 1, you've got a 40 megahertz by channel, it doesn't occur to you that there's a problem. But if you're looking at it graphically, it's kind of nice to kind of it just pops out at you and kind of shows you that, yep, you're kind of interfering with 2 channels, not just 1 there.
Yeah, the graphical format does really make it pop whenever you have overlapping channels. And of course, in 5 gigahertz with a mixture of 802.11a, the old traditional 802.11n, perhaps running on 40 meg wide channels, and 802.11ac on 80 and occasionally 160 megahertz wide channels, it really can be very difficult to pick that out in a tabular format or even on a spectrum analyzer to see what's going on. Next, Erica. Yeah, so this is a very traditional graph of the channel layout, very informative. I expect most people here have seen it, but it shows the channel layout for the 802.11 bands in 5 gigahertz and the channels associated. So for 20 megahertz, the triangles on top, with 20 megahertz wide channels, there's room if we use all the bands for a lot of channels. So a lot of access points in a facility with no overlap. The downside of that, of course, is that we don't have as much throughput on those 20 megahertz wide channels. So as you move down, 40 megahertz wide channels, double the throughput, half the number of channels, still pretty good option for I think most, even fairly dense deployments in offices and hospitals and, whatever your facility is. Still a lot of channels. There's still a really big improvement on 2.4 with its 3 non-overlapping channels. And then we move on farther down, 80 megahertz wide channels. And, we're kind of getting into that channel shortage situation again, where it gets very hard to lay those out so that you don't have adjacent access points sharing a channel. And when you move finally down to the 160 megahertz, you're really in even worse shape than you have in 2.4, 802.11b and G. And of course, once you add the DFS considerations into that, that makes it even worse. And I know you have a lot to say about DFS, Dave.
Yeah, I know that the one thing that we end up seeing a lot of is that as we're going through it, as we were kind of showing us some of like the channels graphs that were coming up, that a lot of times we'll come across, we'll see that people are not using DFS channels, and then when we ask why, it's like, oh, we've got radar here. Well, you should keep that in mind. Then it's like if you're saying that you want to go to 8 to 11 AC wave 2 because of the 160 megahertz wide channels, well, you can't run any 160 megahertz wide channel without it running into the DFS area. So you end up having to, if you want to kind of go there, it's really going to be an issue for you. So definitely something that you have to kind of keep in mind.
Yeah, and we may have skipped over explaining DFS, and that's my fault. But the 5 gigahertz bands, the Uni 2, Uni 2 extended, are also used by some radar systems, and those radar systems have priority on the band. They were the original users of it. So access points are required to listen for a particular signature that it can recognize as radar. And when it hears that, it's required to immediately vacate that channel and move to another one. And of course, that can be very disruptive to clients on it, especially if they're doing voice or video. That interruption as the access point moves to a different channel and the client has to do a forced roam there can be really disruptive to voice or video. So we do see a lot of installations where Uni 2 and Uni 2 extended are just not used. And of course, just a quick look at that chart, if you're only looking at Uni 1 and Uni 3 and for 20 megahertz channels, the ISM band, you're still not in too bad a shape. You've got 8 or 9 channels that you can use there. Pretty good situation. 40 megahertz wide, though, if you're in a DFS situation where you can't use Uni 2 or Uni 2 extended, wow, you're down to 4 channels. So you're almost back into that 2-4 situation. And then with 80, you're down to 2. And at 160, there are no channels available that don't have to comply with DFS regulations. So it's something you need to be taken into consideration. Next slide, please, Erica. Yeah, this is something that I put together because I thought that previous chart really oversimplified the situation tremendously, and it just shows those channels as simple blocks. But if we move down and we look at the 40 megahertz wide or wider channels, we can see that there's a little more going on inside it. And on this graph, it's just a little table that I made up in Excel. Across the top, we see the channel numbers for the 20 megahertz channels. And then the next line, the 40 megahertz wide 802.11 AC, and then the 80 megahertz wide 802.11 AC. Now let's remember that there are a lot of devices out there that are still 20 megahertz wide devices. And so all of the control traffic for in and AC has to happen on a 20 megahertz wide channel so that those legacy clients can hear it. And that's not really a problem. You have a primary channel and an extension channel, or a control channel and an extension channel. There's a lot of language for it. And you can see in that first couple of lines there, we have a couple of, or we have an 802.11n channel represented, and those were named for the primary channel and then a plus if the extension channel was above it, or a minus if the extension channel was below it. So we can see that we've got a 36 plus or a 40 minus there, and those channels completely overlap the primary channel where the control traffic happens doesn't overlap anymore, but still you've got to have both of those channels clear for transmission to happen. So basically those completely sit on top of each other. The next two lines down for 802.11ac, you'll notice that, well, the channel number has changed, and 802.11ac tried to reduce the confusion by all of that plus minus business by just taking the center frequency and making that the channel number. So we can see that we have that same situation where there's still a primary and a secondary. In this case, they're named the same, and that characteristic is inherited from the 802.11n channel behind it. One thing that's different though about 802.11ac, and this is a tremendous improvement for efficiency, is that while you have to have the whole 40 megahertz wide block for 802.11n to be available, nobody else transmitting on it, before the radio will transmit, 802.11ac will check the primary channel and then the secondary channel or channels independently to see if there's any traffic on them. So if that whole 40 megahertz wide block is not available, if somebody else is transmitting on the extension part of it, it will happily transmit on a 20 megahertz wide section of that 40 megahertz wide channel. So it definitely gains a lot more efficiency from that. As you move down, I've illustrated the same situation for 80 megahertz wide channels, and you'll see that once again the channel number has changed, and once again they split the difference, but it has that same 20 megahertz wide primary channel, but then it has two levels of extension. So when it checks to see how wide a channel can it transmit on, maybe it can transmit on that whole 80 megahertz wide block, and maybe some of those parts of that channel are occupied, and it'll fall back to 40 or 20 and still get that traffic through. So it's a big improvement for time sensitive VoIP or video kind of traffic. Anything to add on that one, Dave?
I think you hit on the core thing was the efficiency and the simplicity. One of the things that, you see the 36 plus or 40 minus, it just gets kind of confusing. It's a lot easier to just say like channel 42, obviously. And then the fact of making the system more efficient instead of, one thing about 802.11 is that they come up with things and then they kind of look and see, oh, you know what, we can make this a little bit, a bit more efficient by changing things. So it's kind of like those two common things were kind of greatly improved.
Yeah, absolutely. But it's certainly an effect that you need to be aware of whenever you're laying out a channel plan for a new network or for an existing network. If you're reworking a channel plan, is the way that those 802.11ac channels work. And you can decide, do I really need a dedicated 80 megahertz wide block? In which case you can space those channels out, put the primary in the same place on every one, or if maybe 40 megahertz is enough, you can lay them out more like I've got them on the chart here, where maybe another access point is going to be transmitting in part of my 80 megahertz block, and I'm going to have to fall back. What's our next slide, Erica? Yeah, this is one that we talked about quite a bit when we had the first channel chart up, and the way that moving to wider channels so much reduces the number of channels, and of course the additional reduction that we see if you're avoiding DFS channels. Anything we haven't covered on that one, Dave? I feel like we beat that subject to death.
Well, yeah, I know the thing that you might have, a lot of people have heard is that oh, you want to go to 5 gigahertz, the throughput's better, there's no interference. Really, in a carpeted office where you've got a number of access points, if people are thinking that they want to go to 160 megahertz wide channels, this is really kind of pointing to it. It's like, well, what do you want to do? Do you want to go back to a situation that's worse than 2.4? You know, if you're saying that you don't like 2.4, where are you going to make it worse if you kind of go to 160 megahertz wide? Because, for instance, even if you were saying, you know, I don't have any radar around me, well, you're still at 2 non-overlapping channels, and 2.4 has got 3. So that's even better than. So, you know, I have this chart kind of like really nails that down. Is, you know, if you want to get away from the problems of 2.4, you really want to kind of take it into consideration that your channel widths.
Yeah, and in fact, we've seen some customers that do have or that were using 80 megahertz wide channels in a fairly dense office situation, and in the middle of the night, boy, was it fast. But in the daytime, whenever those channels started filling up, it was really no faster than a 40 or a 20 megahertz wide network. In fact, the 20 megahertz wide network turned out to be, on average, a little bit faster during peak times of the day. So definitely in those dense environments, it's easy to shoot yourself in the foot with those wide channels. Okay, now we've beat that slide to death. What's next, Erica? Yeah, we talked about this a little bit whenever we had the 2.4 up and showing the overlapping channels. And this is from our analyzer product. It shows the kind of the channel widths at a glance. And you can see the pink one there on channel 140 is a 20 megahertz, and then the wider ones are 40 and the wider ones still are 80. If you look over at the right side, over in Uni 3, you'll see that it's really just a mess in there. You've got a 20 meg, 240s, a couple of 80s, all sharing that same space. So, you know, whatever channel planning you're trying to do there is pretty much out the door at that point, and almost guaranteed that somebody's getting stepped on. Anything to add, Dave?
No, I think you hit it just as before, like with 2.4, it really kind of visually pops up at where you're going to have some self-interference.
Yep, absolutely. Next down, we covered that one. I have a problem with skipping ahead. All right, I think that we're ready for some Q&A.
Definitely. All righty. Well, thank you, Mike and Dave, for all of that great information. I definitely always learn something new when I sit on these webinars with them. So thank you. But now we're going to move over to our question and answer portion of the webinar. So you can use your control panel, GoToWebinar panel on this right side of your screen to type in some questions, and they will answer them for you. So we'll let some questions flow in, and then we'll do those here in a second.
There's a question on DFS and when that the AP must vacate the channel. And that's, well, what ends up happening is that when the radar is detected, there's a channel change announcement. It's kind of like a down counter that says, hey, I'm going to move, and then all of a sudden, so that all the clients that are there can then hear it and to say, oh, I'm going to change to a given channel. And once that happens, then it has to wait for 1 minute before that you could go into a channel. So for instance, if before that the access point could actually run on one of those channels, there's not gonna be anything going on for like 1 minute. So that's why we're kind of talking about there's like this disruption that kind of like happens that, you know, a lot of times people, if they know that there's radar, that they might want to avoid. There's a question about how many devices use 2.4 gigahertz. I'm sure you've seen this where most devices will not be 5 gigahertz only, that they're typically 2.4 and 5 gigahertz. And you could probably just go to your Best Buy or whatever store to kind of see that. You end up seeing that the higher end devices kind of like add. They don't say, well, I'm only going to do 5 gigahertz. So you end up finding that there are a lot of devices out there. And then what you might end up doing is that, so we do find that some of our customers then say, well, all we're going to do is from the access point side, go off and run strictly on 5 gigahertz. So there are some devices out there. There are kind of ones that are a little bit older. Where you might see this is in manufacturing, that they'll have older devices. Anywhere where you kind of say, oh, I've got these very, very tailor-made devices and they're a bit older, that you might run into 2.4 still today.
Yep, and if I could expand a little bit, Dave, I think, far too frequently we see in university situations where students come in as freshmen with a brand new laptop, and it's got a lot of memory and a powerful processor and a terrible radio card, maybe 2.4 only, maybe only a single spatial stream, and it's something that that laptop manufacturers will try to save a little bit of money on, and they'll put very low-end cards, radio cards in a laptop, because people don't know that it really makes a difference if you have a card that supports 5 gig and supports AC, supports multiple spatial streams. So it's something I think maybe a little bit unscrupulous, but we see it a lot where freshmen are coming into college with nice laptops with terrible radio cards in them.
We've got another question about how does AP power level interact with channel width? It's kind of an interesting question. That what you'll end up seeing is that if you're actually looking at with the spectrum analyzer, the channel, when you go from, for instance, 20 to 40 megahertz and then on to 80, that the peak actually goes down when you go to a wider channel. That you end up having, in general, you're going to have that wider channel isn't going to go as far as the narrower channels. And then there's a question about interference. Likewise, if you think about interference, if it's something that's random, that's kind of going through it. That's kind of easy when we're talking about on 2.4, because like, for instance, Bluetooth is on there, which is a hopper that'll kind of go through, that the chances on a smaller channel of getting some interference would be smaller. So just from a standpoint of, just statistically where you'd end up having some interference between the two types of technologies.
Yeah, absolutely. The narrower channels are easier to decode as well for the receiver. So a lot of reasons that the narrower channels work better.
Awesome. Well, I think that's it on our questions. And if you have questions still for us, you can send them to me directly after the webinar, and I will make sure to get an answer for you as well. And at this time, just wanted to thank everyone for attending our webinar today. I know I learned a lot of great information, and I'll also be sending you a $5 Panera gift card for just attending. So thank you again. And feel free to come to our other weekly webinars that we have every week with Dave and Mike and some of our other wireless staff here at 7 Signal. They're all really great and packful of really amazing information. So we'd love to have you back on a demo. And if you have any other questions, feel free to reach out to myself, Don Cook, and we'll get those answered for you. But with that, thank you so much, everyone, and hope you have a great rest of your day.
Thank you, everybody.